linear relationship with the molality, the concentration that we just talked about. So if you can figure out the molality there, and you know the constant for the particular solvent that we're using, you can figure out what's the new boiling point of the solution, what's the new boiling point, freezing point of the solution. Okay, so that's the calculation involved in here. Now the colligative properties there is that some of the physical properties of the solution, some of the physical properties of a solution only depend on the number of particles that are present, and in terms of the solute and solvent there. So if you look at the definition of molality, we have number of moles per kilogram of solvent. So that's a relative ratio. That's a ratio between the number of particles of the solvent versus number of particles of the solute. So number of moles, each mole has 6.02 times 10 to the 23, that many nanoparticles there. And kilogram, if you know what the solvent is, you can convert it into moles as well. Mass to mole, it's a mole to mole ratio there. And that's the relative particles of solute and solvent in that solution. So that concentration gives you that ratio there. So for the colligative properties, we refer to vapor pressure. Now, when we define vapor pressure, it's when you have a volatile liquid, you put it in a closed container. At certain temperature, that liquid will vaporize, generating a pressure, and that's a vapor pressure. So how does the vapor pressure of a solution, say water dissolved with some sugar dissolved in there, or water with some sodium chloride dissolved in there, how does the vapor pressure of that solution compare to pure water? Now in chapter 5, when we're talking about the vapor pressure of water, we have measured the vapor pressure of water in every temperature. And we know the vapor pressure when it's at 0 degrees, it's a certain value there. When it's at 100 degrees Celsius, it's 760 millimeter mercury. That's when the water starts to boil. So we want to take a look at it. How does the vapor pressure compare between the solution and pure solvent, and also boiling point? Okay, boiling point is the temperature in which the vapor pressure of the liquid equals to the external pressure. We also introduced yesterday the normal boiling point. Normal boiling point by definition is when the external pressure is equals to 760 millimeter mercury. And a freezing point, that's another physical property, depends on the relative number of particles in the solution there, and then osmotic pressure. So we are able to quantify the changes for these four properties there, and these four properties are collectively called colligative properties of the solution. And there are other properties involved, and it has something to do with the number of particles, relative number of particles of the solute and solvent. And the textbook mentioned that, but in this particular chapter there, we want to talk about these things there. Now, for the change in vapor pressure, if you want to quantify it, that follows the Rawls law. Now, we don't need you to do calculation, but this is something that we just want you to, that M word, memorize. So vapor pressure is the pressure exerted by the vapor when a liquid in a closed container is at equilibrium with the vapor there, and that's how we define vapor pressure. So if you have something dissolved in a pure solvent making a solution there, the vapor pressure of the solution is lower than the vapor pressure of pure solvent. So if you have a cup of water versus water with some sugar or salt dissolved in there, the vapor pressure of the solution with the sugar or salt dissolved in there is lower than the pure substance, than the pure water there, than the pure water there. Okay, so vapor pressure is lower when something is dissolved in the solution. Now, do we have to quantify? Well, we do have ways to quantify how much is the vapor pressure going to decrease, but in this case, we don't need you to do calculation. Just remember this conclusion: vapor pressure of a solution is lower than the vapor pressure of the pure solvent. Okay, and so that's the change in vapor pressure. Now, so the reason behind that is because the more solute particles present in the solution will result in a lower vapor pressure of the solution. Okay, so that's the change in vapor pressure. And now, out of those four colligative properties there, and we also talk about the freezing point. Now, the freezing point is actually lowered as well. So vapor pressure is lower for the solution compared to the pure solvent, and freezing point is also lower. We use the term freezing point depression. The freezing point of the solution is depressed because of the presence of the solute in that mixture there compared to the pure solvent. Now, this is something that we all have experience with. And if you put some water in the glass, and you put that glass in the freezer, now when water starts to freeze up, volume expand. We talked about that. The volume expansion is because of the hydrogen bonding. So hydrogen bonding, when the water freeze up, and it results in a larger volume there. Now if you just have water in that glass there, this is what's going to happen there. When as volume expand, and then the container may be cracked. Now if you put some antifreeze in here, well, that will keep the liquid in the liquid form without freezing up. So the application here is that you add some chemical in water, you prepare a solution. The solution will have a lower freezing point. As a result, the liquid will stay in the liquid form instead of freezing up. Now, if you have ever been to, in a cold winter day, if you have been to a harbor where the fresh water from the river meets the salty water from the sea, all you will see in the cold winter days, the freshwater part is freezing up. The seawater part is actually staying in the liquid form, and they're not freezing. So the reason for that is because there's a lot of salt dissolving salt in seawater compared to the freshwater from the river. So that's one of the things that that you will notice there. And also this past winter we got quite a bit of snow there. And every time when it snows, you see the trucks on the road and they spread sand and salt on the road. The reason that they put sand in there is to increase the friction, and the salt will dissolve in water, making water solution a solution containing salt. That will lower the freezing point of water by a couple of degrees there. In that case, that will keep the water in the liquid form instead of freezing up. So that's the application there. And one application that I could think of, is that I think it's the December of 2012. I want to go back to China and visit my parents, and I told you I have chickens. They need water. So I was thinking, well, maybe I can use the freezing point depression, add some salt to the water, and while I am away, I can make a solution there. But the thing here is that how much temperature, how much the freezing, how much can you depress the freezing point depends on how low the temperature you want it to be. So I look at the weather channel here. The lowest temperature happens to be -8 degrees Celsius. So I did a calculation. I have a gallon water, and for a gallon water, 3.78 liter of water. If I need the freezing point of that solution to be below -8 degrees Celsius, and when I calculate the molality, I realized that I have to put more than 2 pounds of salt in that water. And I think my chicken would hate that, so it didn't work out. And I have to ask my neighbor to come over and change the water every day and replace the water and put it in there. So, but that's something that you can keep, and then you want to keep in mind there. And you can lower the freezing point solution by adding salt there. If it's only a couple of degrees, then you may be able to do that, and then putting some salt in there, and maybe lower the temperature by a couple of degrees there. So freezing point is lowered. How about boiling point? If you have pure water, we know pure water under normal condition, 760 millimeter mercury, pure water boils at 100 degrees Celsius. If you throw something in there to make a solution, the boiling point is increased. We can actually quantify the changes in boiling point and freezing point by using a mathematical